What would you do if you woke up tomorrow to find all technology rendered useless by a G5 solar storm? Well, the Earth is about to be hit by a very unusual solar storm. This intense solar flare serves as a stark reminder of the dangers posed by variations in the Sun's surface conditions. The modern world relies on reliable electricity infrastructure, communications, and navigation, all of which can be disrupted by powerful solar storms. As the world stands on the brink of technological collapse, one man dares to step forward with a dire warning. Bill Nye warns of an unprecedented G5 solar storm, a cataclysmic event that will plunge civilization into chaos and darkness. As the G5 solar storm approaches, we must ask, is our civilization ready to withstand a disaster of this magnitude, or will we be consumed by the darkness that awaits? Join us as we explore Bill Nye's final warning for an extreme G5 solar storm. The huge solar storm that Earth has experienced in recent days is a clear illustration of the immense impact the Sun has on our world. An enormous solar flare has triggered the strongest geomagnetic storm ever recorded in Earth's atmosphere. This storm may disrupt power grids, communications, and navigational systems, and could even cause the northern lights to be visible as far south as Florida and Southern California. As the Sun's constant stream of radiation bombards Earth's magnetic field, the consequences may linger into the weekend. The NOAA, which monitors space weather, has issued an extraordinary storm watch, the first such advisory in 19 years, and has since raised it to a warning because the solar activity is so intense. At least 5 of the sunspots that the organization has been tracking have begun to produce eruptions that might potentially impact Earth. The storm's most noticeable feature, the northern lights or auroras, will be seen by many people across the globe. However, governments and businesses will also be watching to see how the event affects critical infrastructure such as GPS, radio communications, and power grid resilience. We had a taste of the Sun's destructive effects on September 2, 1859. Around the world on that day, marine compasses stopped functioning, leading to the loss of some ships, and some telegraph lines caught fire, disrupting the networks. Notably, auroras were seen by folks in Mexico and the Caribbean, which is quite far south. What occurred on that day more than 16 decades ago was likely an intense geomagnetic storm, according to scientists today. Since then, the 1859 storm has become known as the Carrington event. The event was named after British astronomer Richard Carrington, who discovered the solar flare that caused the storm. Richard Carrington was a well-known British astronomer of the 19th century. His focus was the Sun. He was the first to discover that the Sun doesn't spin as a solid body but that solar material travels quicker at its equator than at its poles. He also found out where the Sun's north and south poles are. He discovered that the dark spots on the Sun's surface, called sunspots, vary in latitude over the 11-year solar cycle. Carrington and Richard Hodgson saw the first bona fide solar flare. Carrington witnessed a brilliant burst of light on September 1, 1859, while studying sunspots. Scientific consensus today holds that he witnessed the solar system-wide shock waves caused by the massive coronal mass ejection, an explosive event that occurred close to the Sun's surface and was propelled by magnetic field lines. The next day, a massive storm hit Earth's magnetic field. When the Sun is in the final stages of its 11-year cycle, coronal mass ejections are more abundant on its surface. It is now standard practice for our spacecraft to record coronal mass ejections. Although there were suggestions that coronal mass ejections existed in the 19th century, their discovery was still a ways off. It wasn't until 1971 that coronal mass ejections were detected by the Helios satellite using ultraviolet studies. The Royal Astronomical Society was promptly notified of the flash by Carrington. He likely didn't give it much more consideration until the next day when the geomagnetic field went into overdrive due to the fast-moving solar particles making their way to Earth. The solar particle burst released around 10 to the power of 35 electron volts of energy while buffeting, compressing, and distorting Earth's magnetosphere, encasing the planet in a roaring, writhing mass of high-energy particles. That's a 10 followed by 35 zeros. This amount of energy is equal to a 10 megaton nuclear bomb. It's also equal to the amount of energy the sun releases in about 10 seconds. As far as anyone knows, it was the strongest solar event in history. An urban legend states that a telegraph operator was paralyzed in one arm after he woke up from a shock that had rendered him unconscious. Although there is no evidence to support this claim, it is absolutely not ruled out. The extreme geomagnetic storm subsided the following day. Work began to repair telegraph networks, and everything went back to normal as the dazzling auroras disappeared from view. To understand the 1859 event, we must understand the solar cycle. German amateur astronomer Samuel Heinrich Schwab had just discovered the 11-year cycle in 1843. Schwab had been observing the sun for over 17 years when he noticed that the number of sunspots on the sun's surface varied over time. He also noticed that the period of this variation was about 11 years. Our knowledge of the sun was advanced by Schwab's finding. As a result, we now know that our star is, in fact, quite dynamic and subject to constant change. Additionally, we know that February 1860 was the peak of solar cycle 10. Since Schwab tracked the solar cycles, the Carrington event happened just months earlier in September 1859. The solar cycle, which lasts 11 years and reaches its climax when the sun's north and south magnetic poles switch positions, is caused by the sun's magnetic field. There may be a few years of enhanced coronal mass ejections and other intense solar phenomena around the sun's zenith of each cycle. And we're currently in one of those periods. With each coronal mass ejection, the sun releases about 1 billion tons of material into space, and occasionally this solar material is actually headed in Earth's direction. A geomagnetic storm, not always a powerful one but nevertheless a remarkable occurrence, occurs when it reaches Earth. When this happens, high-energy particles from the solar wind smash against Earth's magnetic field. March 1989 was the year of another major solar storm that knocked out electricity to much of Quebec, Canada. The province's electrical grid was overloaded by currents brought forth by a coronal mass ejection that struck the planet. For over 9 hours, millions of Quebecers were without light, and the province's economy took a hit worth hundreds of millions of dollars. Minor interruptions were also caused by the storm in other regions of Europe and North America. This event showed how vulnerable modern infrastructure can still be to space weather. The 2003 Halloween storms began on October 19 and reached their height just before Halloween, thus the name. Satellite communications, GPS systems, and power grids were all affected, and auroras were seen as far south as Florida and Texas. Radiation levels were so high that planes had to change their routes, and the astronauts on the International Space Station had to seek refuge. The greatest violent solar storms of the first space period occurred in 2000 during the Bastille Day event, which was named after the French national celebration on July 14. Approximately 24 hours after a large solar flare had burst, Earth was hit by a coronal mass ejection. Intense auroras were visible across North America and Europe as a result of the storm, which also momentarily crippled a few satellites. It wreaked havoc on aviation and marine navigation by interfering with radio communications and GPS signals. One of the lesser-known but highly impactful solar storms happened in May 1921, affecting the northeastern US and parts of Europe. Geomagnetic disturbances were caused by the massive coronal mass ejection that impacted Earth. Disruptions to telegraph and telephone lines occurred, and fires broke out at some stations as a result of induced electric currents. Additionally, it disrupted transportation due to the widespread breakdown of railway signals. So, how strong is the current geomagnetic storm? Streams of energetic particles are released into space from the sun's surface during massive outbursts. On the other hand, such eruptions might not even reach Earth as it circles the sun, given how massive the star is. But when these particles create a disturbance in Earth's magnetic field, it is known as a geomagnetic storm. Using a scale from 1 to 5, NOAA assigns storms a G rating, with 1 indicating a mild storm and 5 an extreme one. The most extreme storms can cause widespread blackouts and damage to infrastructure on Earth. Satellites may also have trouble orienting themselves or sending or receiving information during these events. The current storm is classified as G5, or extreme. It is caused by a cluster of sunspots, dark, cool regions on the solar surface that are about 16 times the diameter of Earth. The cluster is flaring and ejecting material every 6 to 12 hours. The scientific community is bracing for a series of shocks. Why is this happening now? The Sun's activity peaks every 11 years, and we are currently in the midst of that peak. There have been 3 other major geomagnetic storms noticed so far in this activity cycle, which started in December 2019. But none of them were anticipated to have an impact on Earth significant enough to trigger an alert or warning. According to Bill Nye and NOAA officials, the current storm is being caused by the greatest cluster of sunspots witnessed in the solar cycle. They added that the activity in this cycle has outperformed initial predictions. The Sun's rotation will force this cluster to be orientated in a way that is less likely to impact Earth, but it is still projected to produce more flares and expulsions. Scientists are unsure if the sunspot's potential reappearance on the Sun's left side in the next weeks will trigger yet another flare-up of activity. Are we to be concerned? No one on Earth's surface needs to be worried about solar storms. Even though these storms are terrifying to think about, they pose no threat to humans so long as we stay on land and the atmosphere protects us. Keep in mind that since the Sun and Earth came into existence, there is every indication that solar storms have been occurring for billions of years. In that case, they would be responsible for the evolution of all life on Earth. When it comes to space, how dangerous is a solar storm? Radiation poisoning can be caused by extremely high-energy particles, which are delivered by coronal mass ejections. This includes humans and other mammals. They would be dangerous to unshielded astronauts, say astronauts traveling to the Moon or Mars. Large doses could be fatal. Solar storms can be dangerous to our technologies, though. Charged particles from a coronal mass ejection can slam into Earth's atmosphere, damaging or even destroying orbiting satellites and exposing planes in the sky to radiation. Their presence has the potential to interfere with navigational and phone systems. Entire cities and even regions have been blacked out due to their ability to disrupt power grids. People talking about power failures from solar storms always point back to March 13, 1989, 35 years ago, the power failure in Quebec, as well as across parts of the northeastern U.S. that we mentioned earlier. This event cut off electricity to over 6 million people for 9 hours. But it's possible for solar storms to be even more powerful than the one that caused the 1989 Quebec and U.S. Northeast blackout, such as the Carrington event or the 1859 solar superstorm. How would our lives be affected right now if a Carrington event were to occur today? Our world is totally different now. All around us, our technology is sophisticated and cutting edge. In a world where the internet has replaced telegraph lines as the primary means of communication, our lives are more interconnected than ever before. The first undersea transatlantic telegraph cable came just a year before the Carrington event in 1858. It connected North America with Europe for the first time, allowing news to propagate around the world faster than ever before. Today, most of the world's internet traffic flows through undersea cables of vast capacity. Existing cables flow with ever-multiplying streams of ones and zeros, the telegraph songs of the digital age. Computers manage our society. They permeate every facet of society, from healthcare to entertainment to electricity grids to banking. Everything from toasters to TVs, telephones to automobiles, owes its existence to the invention of the integrated circuit, which ushered in the modern era. If another Carrington-type event were to cause the Earth's magnetic field to generate massive electrical currents, what would the consequences be? Could national electricity grids be affected? Much larger-scale power grid failure and electronic circuit burnout than the Quebec blackout of 1989 would likely occur as a result of a solar storm. If the electricity went out, millions upon millions of people would be unable to charge their phones or use any electronic gadgets. A Carrington-like storm could affect nearly every important part of contemporary infrastructure at the same time, including power, food, water, transportation, security, and communication. It would also cause widespread blackouts, which would disable pumps that are vital to the water supply. On a good day, it's easy to see how issues in many areas might amplify each other due to the amount of impairment. How would the electricity grid fare if the storm occurred in the thick of winter, when the cold might be fatal? The internet could also be significantly affected by a storm. Undersea cables transmit most digital traffic across continents, but they contain components that could be damaged in a major geomagnetic storm. Then the internet could only operate on a much smaller scale within private networks. Those in turn might be compromised by the storm in other ways. The impact of a major solar storm would vary greatly around the world, depending on a region's power grid, proximity to water, location relative to the Earth's magnetic field, and even geology, which determines how good of a conductor the ground is. China, the United States, and Australia may be more vulnerable to power outages than most of the world due to a mix of these factors. The metropolitan corridor spanning Washington, D.C., and New York City has been described as particularly vulnerable. In space, satellites would also fail as their electronics fried. On a far lesser scale than the Carrington event, this has occurred multiple times during geomagnetic storms. A coronal mass ejection in March 2022 caused the failure of 40 SpaceX Starlink satellites. The most recent incident, they launched the day before the storm hit, but it wasn't their electronic systems that failed. One effect of a geomagnetic storm is to increase atmospheric drag on the satellites. It pulled the satellites back toward Earth, where they burned up in the atmosphere. Satellite only carries around 1% of all internet traffic globally. Nevertheless, satellites facilitate all financial activities, including those using ATMs and credit cards, as well as the transmission of banking messages. Widespread communication loss would be inevitable. There would be utter chaos for a while, and recovery might take years. Professionals have attempted to conceptualize the effect. Solar storms alter the Earth's magnetic field, which can lead to massive currents in power lines, which can damage or destroy transformers and electrical systems. According to studies conducted in the US alone, tens of millions of people might lose electricity for weeks, months, or even years due to a big solar storm. There would be trillions of dollars worth of economic harm. Bill Nye claims that these estimations are inadequate. The real impact is beyond the scale of our comprehension. It's way, way beyond that. In case you find this to be an overwhelming prospect, allow us to pose a crucial question in order to help you put things in perspective. Just how likely is another Carrington event? After all, it's been 164 years since the last one, so do we view it as a blip, or do such events recur on longer time scales or perhaps even at regular intervals? Is it possible to foretell when the next storm will hit and how severe it will be? And most importantly, how much warning would we receive of a catastrophic catastrophe similar to Carrington? First, we need to address the root cause of the issue, which is coronal mass ejections. Indeed, our understanding of them has greatly expanded since their discovery in 1971. On the other hand, coronal mass ejections can fool you. Although coronal mass ejections are more common during solar maximum because the sun's magnetic field reorients at that time, our understanding of the processes that cause them is yet insufficient to predict when they will actually occur. Consequently, the likelihood of a repeat of the Carrington event is completely unknown. The frequency with which these occurrences happened prior to 1859 is similarly unknown to us. Such storms likely remained unrecorded prior to the invention of electric grids and equipment, with the exception of reports of spectacular auroras. How much warning could we have of a devastating storm that could rock our society? The good news is that scientists are well aware of the risks. They are diligently employing AI to predict the worst possible times and places to strike. Dagger, developed by NASA heliophysicists, can only alert us to impending storms about 30 minutes in advance. We now have the sun under constant observation from Earth and satellites. It is challenging to predict the precise amount of material that will strike Earth when the Sun emits a coronal mass injection. We have no idea which ones are harmful. To put it plainly, whatever the case may be, scientists keep a close eye on the Sun from all across the world, including the Space Weather Prediction Center. It is their job to spot solar storms that could have an impact on Earth. Ultimately, the solar storm must occur on the Sun's surface that faces Earth for it to impact Earthlings. The coronal mass ejection often reaches Earth several days after such an outburst. Satellites can temporarily disable their systems to avoid harm when a large coronal mass ejection is approaching. It is also possible to modify Earth-based power systems to offer additional grounding with prior notice, and so on. Scientists and governments are starting to pay greater attention to the problem, with the hope of developing methods to resist the Sun's intense rays. Getting a better, more complete picture of the Sun's magnetic field is crucial to keeping hope alive. We may be able to foresee the future's devastating geomagnetic storms someday. The same precautions taken to protect spaceship electronics from electrical currents can be taken to protect our power grids and technological infrastructure. But it can't happen until global governments acknowledge the risks and take action, which in turn requires substantial funding. So far, they have not allocated nearly enough money and resources to protect us from civilization-destroying asteroids or, of course, the effects of climate change. There's little reason to be optimistic that those in power will take the threat of another Carrington event seriously. Our greatest bet in the face of such a possible calamity is to increase our knowledge of the Sun-Earth system, keep an eye on the Sun's activity, and work on improving our space weather prediction abilities. The more familiar you are with the system, the more accurate your predictions will be, much like with regular weather forecasts. Concerning our star, this is not a simple undertaking. In addition to better understanding the Sun and its complexities, scientists need to learn how solar emissions interact with Earth as they move through space. Our space weather forecasts lag behind the general weather forecast by around 50 years. That is why it is crucial to send spacecraft like the Parker Solar Probe, which made history by touching down on the Sun. Launched in 2018, Parker has already made several discoveries about how the Sun transports energy outward into space. In 2022, Parker even flew directly through a coronal mass ejection. The spacecraft's data have helped scientists improve their ability to predict exactly when an event at the Sun will later reach Earth. Bill Nye says that determining the time is crucial since it is the initial stage in establishing an early warning system, which would aid in preventing the worst-case situation. Yet he warns that our current projects are not enough. Parker is not designed to act as a full-time warning system, and it can only study the Sun from one angle at a time. He suggests a constellation of satellites around the Sun, almost like Starlink around Earth, in order to completely survey the Sun and always be ready to relay warnings back to Earth. We need to begin with expansive ideas. We need to take risks. Solar activity is not all bad news, despite the fact that it has the ability to destroy Earth. Since solar activity may have accelerated the emergence of life on Earth, it may be the source of our own existence, according to some research. Ironically, solar activity also keeps us safe. Emissions from the Sun shield us from even deadlier radiation that comes from the galaxy at large. Therefore, future space missions that will take place outside of Earth's magnetic field may find that periods of maximum solar activity are the most favorable. Solar storms pose the greatest threat to astronauts' safety from galactic hazards. Yet when the Sun is active, it acts as a greater buffer. That timing would put a mission more at risk of getting hit by a coronal mass ejection. But if we could monitor and predict solar weather, it might be possible to minimize local threats while protecting astronauts from galactic ones. Humanity has options. What we do now could have far-reaching consequences when the next major storm hits. A more resilient design for satellites against geomagnetic storms is within our reach. We may follow Quebec's lead and fortify our electrical infrastructure, particularly our transformers, which the province spent more than $1 billion on following the power outage. Though U.S. electrical transmission providers recently began this process, their precautions seem to be designed with weaker storms in mind, not Carrington-level events. More funding for solar research is also an option. NOAA's Space Weather Follow-on L-1 Range 1 mission and NASA's Interstellar Mapping and Acceleration Probe will both monitor the Sun and provide data to help predict space weather. Both are set to launch in 2025. Meanwhile, the Parker Solar Probe will make its closest approach to the Sun in late 2024. With a speed of about 435,000 miles per hour, the NASA spacecraft will surpass its own record as the fastest man-made object. The principal mission of the Parker spacecraft will conclude in 2025, but the probe is in excellent condition, like we launched it yesterday, and scientists intend to extend its operation for as long as possible. After all, a mission like Parker is a rare opportunity. The data it collects will be crucial to efforts to understand our Sun, and they may ultimately help decide what impact the next big storm has on humanity. Are we too dependent on technology, and could a disaster such as the G5 solar storm serve as a wake-up call to re-evaluate our reliance on it? Thanks for watching another episode of Space Trailway. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.